Our next speaker is Jim Lococo from Mount Sopris with Borehole Geophysical Logging.
Thanks for your attendance today, by the way. Appreciate everybody being here. And I'd like to acknowledge my co-authors here on my presentation, Timo and Wendy. They might be in this room somewhere. I haven't seen them, but they could be. Anyway, the last 10 years of slim hole borehole geophysics has seen a lot of advances. And most of them I'm not even going to talk about today. I'm going to talk about ones that I know very little about, or something about. Anyway, borehole imagery tools, for example, has reached resolutions that allow investigators to visualize true color borehole wall attributes, grain size features, rock fabric, structural integrity. These slimline tools allow us to perform high resolution fracture characterization, casing thickness evaluation, along with a lot of other applications. Other high-end borehole logging techniques like nuclear magnetic resonance has evolved with much smaller diameter tools. An oil-filled NMR tool versus a mining tool is, you'll see a picture later, it's much different. They're commercially available today. These newer, highly innovative sondes operate on standard, commonly available geophysical wire lines, thus allowing entry into some of these other areas. Advances in slimline borehole gravity tools over the past several years has found importance in mining, we all know about that, including bulk density determination, rock properties, and verification of surface and airborne gravity anomalies, for example. Advances in spectral gamma, our spectral induced polarization, in this case, is revealing this unique sensitivity to interfacial properties of porous materials. SIP, as it's called, spectral induced polarization, is sensitive to fundamental pore geometry properties controlling fluid flow, and recent case histories indicate that this measurement could be a permeability tool. Well, so a couple slides on that. New generation XRF tools have been developed further in the determination of minor and major concentration of elements in boreholes. Well-calibrated spectral gamma tools, we've all seen spectral gamma tools, have transformed quite a bit over the past 10 years. Unfortunately, I'm not going to talk about borehole gyro tools because it's just too much, but there's been a lot of borehole gyro development. So these techniques, NMR, SIP, XRF, and others have had a lot of evolution. So we'll look at a few slides now. Okay. One of the things that, of course, has happened is stackability. Geophysical logging tools have been stackable since the 1980s, but the last decade has presented us with innovative mechanical designs, improvement in telemetry performance, and other electrical wire lines, allowing us to continue combine slimline logging tools, that is, in custom configurations to acquire more physical parameter properties in a single logging pass. Nowadays, sondes are combined according to specific requirements of the application, hydrogeology, mineral and mining applications. This flexibility saves time and cost in the field. Some of these linkable sondes are considered bottom, some are inline subs. Some of the sub-assemblies, for example, the E-log, you can get a spontaneous potential, a resistance, several normal resistivities, and induced polarization with one sonde. So these concepts and the evolution of customizing downhole measurements is something that has shown great improvement over the past 10. Sorry. Some of these custom stacks, for example, there's a graphic here on the bottom which has a natural gamma, a magnetic susceptibility, and an induced polarization, all taken in one logging pass, and this happens to be from a iron mine in central China. So this is pretty useful because, as we know, any of you in here that have worked with boreholes knows that they are a hostile environment, and they have a tendency to eat logging sondes every now and then. Some other possibilities here include Acoustic Televiewer, Optical Televiewer, Density, Neutron. These are all bottom subtools. The NMR tool that I'm familiar with is also a bottom sub-tool, so it has to be on the bottom of a stack. For example, you can stack natural gamma with a nuclear magnetic resonance to get a nice sort of synergy of log. Okay, so let's talk about some of these techniques. Let's talk about the evolution of borehole imaging tools over the past 10 years or so. They provide a high-resolution, direct or indirect 360-degree image of the unwrapped borehole wall. Tools are equipped with orientation sensors, measuring tilt and azimuth, that record images that can be oriented with respect to magnetic north to the high side. I've highlighted here in yellow some of the key changes or developments or enhancements that have occurred the last several years. You'll see on the right there 1,800 pixels around the azimuth of the borehole. What that allows us is really high resolution imagery down to grain size mineralogy type applications. The graphics here kind of show that. For the acoustic televiewer on the left, you see that one of the features that have improved over the past several years is the rotation of the acoustic mirror that allows for faster logging up to 35 revolutions per second there. The optical televiewer has gained a lot of popularity over the years. Provides a high-resolution it's a high-resolution digital camera with a fisheye and LED light source which deliver high-quality, true color image of the wall. Moreover, the exposure can be adjusted by the operator in the field to get some decent quality in difficult wells. The left image here is a comparison between two optical images recorded in the same well, one in 2009, the other in 2015. The first generation is on the left track, second generation on the right track. This 1,800 pixels around the circumference is equal to about a 0.26 millimeter arc width. So that's pretty high resolution. Wendy, am I saying that right? Is that right? Okay, thank you. The right image is an analysis of mineral phases, grain size distribution, and porosity can be performed with these optical images in conjunction with dedicated software applications with colorimetry methodology. This is another optical televiewer comparison from a mudstone in the Mount Sopris test well in our backyard. This is a 2007 image versus a 2017 image. Imagine what the 1997 image looked like, and the 1987 image. They probably didn't exist back then. Borehole video camera, right? This is another recent optical televiewer image through an andesitic and lithic tuff at a copper mine in Arizona. This borehole was HQ, so 102 millimeter borehole, and you can see pretty good resolution here. This was only collected at 600 points per turn. So but the trade-off here, of course, is higher resolution, lower logging speeds. So this could have been logged at even higher resolution to have a better image. Another recent generation optical televiewer log, this time through South Florida karst. The nominal diameter of this well, 156 millimeter, resulting in an azimuthal resolution of about 3 millimeters. The image resolution is high enough now to identify microfossils. You see them in this slide. So the U.S. Geological Survey is dating these bugs so they can date the strata. Basically, there's two different types of acoustic imaging tools available. First, tools that have a rotating transducer, and secondly, tools with a fixed transducer and a rotating acoustic mirror, as shown in this slide. The rotating acoustic mirror is over there, and for those on this side, it's right there. It's hard to point to two slides here. 10 years ago and earlier, very slow logging speeds led to limited acceptance of these tools in industry. Nowadays, logging speeds of acoustic borehole imaging tools has increased significantly, up to 6 or 8 meters a minute, depending on the resolution that you select in the field. This is definitely due to the implementation of new components in acoustic heads, stepper motor, which allows faster rotation, which I showed a couple slides ago, In open hole applications, recorded parameters are travel time and the amplitude of the reflected echo. If the velocity of the borehole fluid is known, borehole radius can be derived, and two-dimensional image of the borehole radius can be generated. Besides determining borehole diameter, these images are very useful in the identification of washouts, fractures, stress analysis, and other borehole wall attributes. Additionally, the amplitude of the reflected echo is a semi-quantitative measurement that can be used to derive physical properties of rocks exposed on the borehole wall. That's a nice feature. The combination of the two images allows for a dedicated lithological and structural analysis of the borehole wall with appropriate software. Common application for such tools, for example, is the detection and quantification of fracture zones, geotechnical, hydrological, and mining investigations. Another example here, in casing. Casing inspection applications of slimline acoustic imaging tools has developed quite a bit. Among other solutions, exchangeable acoustic heads have been designed. Consequently, the same tool can be employed for diameter ranges from, say, 73 to over 600 millimeter diameter, simply by exchanging the acoustic head as illustrated in these examples. The left example is 73 millimeter tubing, and the right example is 508 millimeters. And these images show features on the casing to evaluate casing. The thickness and qualitative cement bond information is valuable for well abandonment programs, plugging projects. Other applications are for the evaluation of well integrity, new wells, and during their life cycle. The availability of high temperature components is out there. So these televiewers can be used in boreholes up to, say, 270 degrees C or even more. There's a family of tools available for different temperatures that you may require. Nuclear magnetic resonance has evolved with much smaller diameter tools running, once again, on standard available geophysical wire lines, thus allowing entry into the mining and groundwater communities. Mine dewatering projects. This could be an area where the NMR tool may have some use in the future. This slide illustrates, the difference between an oil field NMR tool on the far left and an NMR tool that's used in the water or mining industry adjacent to it, and of course my stick man there next to that. Nuclear magnetic resonance logging makes use of a strong permanent magnet and a weak oscillating magnetic field from precisely timed bursts of electromagnetic energy at specific radio frequencies. Between these pulses, an antenna is used to detect decaying spin echo signals from hydrogen nuclei in resonance with that permanent magnetic field. So applications clearly include moisture content, specific yield, dry weight density in iron ore deposits, for example, to determine the blend for feedstock to the crusher as a quantitative resource, picking closed and open fracture features in combination with the televiewers, developing dewatering strategies around underground coal mines, for example, and mapping aquifer hydrogeology as a guide to develop comprehensive groundwater management programs and strategies. Other applications include characterization of brine hydrogeology to determine economic viability and shaping development strategy in mining operations, mapping of coal seams. Borehole NMR is specifically tuned to sense pore network fluids only, enabling precise determination of rock total porosity, moisture content, mobile fluid content, specific yield that is, bound fluid contact or specific retention, and permeability. Permeability is a big deal in many industries. Sample log here. Stacked with a natural gamma. Data is inverted here to give a continuous T2 distribution for the logged interval. That's the third track there from the left, the bluish track. The red track there is natural gamma. Higher natural gamma, of course, are the clays. And the third track, the blue one there, the T2 distribution, is the clay. So you see the differences between bound water, mobile, pore water, and free fluid. Spectral induced polarization. In 1998 or so, a thorough yet pretty valuable summary of research on the spectral IP method, noting that the colorful history of IP goes back to the Schlumberger brothers many decades ago. That said, SIP technology is a relatively new technique in exploration in near-surface geophysics, and borehole SIP really has not come to the mainstream yet. However, proof of principle testing, validation is and validation is ongoing. So this is something maybe exploration 2027. I'm sure I won't be here then, but somebody may talk about it then. Borehole SIP is being developed by several universities. One of the main universities here is Rutgers and others, and they're leading the way in the advancement of SIP in the borehole environment. And Chemna, in fact, if you look at the manuscript, I have an extensive bibliography that goes into more details about some of these advancements in these borehole techniques. Anyway, Chemna described some of these results of laboratory testing. Slater and others reviewed geophysical literature focusing on the estimation of saturated hydraulic conductivity from SIP measurements. The left graphic on this slide is from Slater's work. So you can see that in the white area and the sort of the left is the classic resistivity, where you can use Archie's equations and estimate permeability, for example. IP uses typically single frequencies, and we get chargeability curves, and we draw reference about many things. But the spectral induced polarization uses many frequencies, from maybe 0.001 hertz to 10,000 hertz, sweeping the formation, and we get information, the return signs, and we look at the phase and amplitude differences, which is shown there. Oh boy, am I that far behind?
Wasn't watching the time, to be honest.
Okay. Let's see. We might skip the. Okay, let's go to.
You're at your 0 time. So
Okay, I might as well talk about borehole gravity for a moment, since I see borehole gravity people here. But borehole gravity has been applied to oil reservoir evaluation since the 1950s. Density, logging tool density only sees a few inches. Borehole gravity sees a lot more. The graphic in this slide is a basic schematic of a gravity sensor and an inclined spring and lever arm mass. Oh, I'm sorry. Darn, thank you for that. Okay, there's my borehole gravity slide. Thank you. Sorry. Anyway, I'm not a gravity expert. There are others in here, and I encourage you to talk to them about borehole gravity, but it has really evolved over the past 10 years. And, I was looking at the internet a couple nights ago, and I read a quip by somebody who said the high sensitivity of gravity, to put it in perspective, is equivalent to trying to weigh an entire whale in order to determine the weight of its whisker. That's the kind of gravity resolution I think people are seeing today. And like I said, I'm no expert. You've talked to others at the conference here. XRF advances the past 10 years have also seen some changes. And basically, it's used in the determination of minor and major concentrations of elements in boreholes, blast holes, ore seams, tailing pipes, and so forth. Currently, available tools only see or resolve elements between about a Z of 13 aluminum and uranium, Z of 92, but with good reliability. However, there's a few pitfalls there. You'll see in that picture in the middle, there's something called a mud plow that is used to scrape the borehole wall so the XRF window can have contact with the wall to get good information. That's kind of a big drawback, but it is being worked on. So, do I have time to talk about spectral gamma?
You're getting tight.
Okay, I'm getting tight. Spectral gamma, just real quickly. You see on the left slide, classic window stripping method. On the right side, you see new processing techniques using something called Medusa to characterize the entire spectrum to get better spectral gamma data. Talk to me more later on that one. I want to talk about software real quick. Software advances for well logging analysis and presentation have undergone a lot. Basically, the left figure shows 5 major shifts in the information technology. It's important to note that the essence here is that data is so comprehensive and intense that you can't really characterize or evaluate or interpret geophysical data on your iPhone or iPad. You need a different kind of computer system. And there's pictures here of people trying to develop geophysical processing software with handheld devices, and I personally don't think that's going to work. I don't know how others of you feel, but since I'm out of time here, I'm going to go ahead and go to my conclusions. And the main conclusion is what's next? Slimline neutron generator without an americium source? That would be a nice way to get porosity. I didn't even talk about logging while drilling or measurement while drilling, but there's lots of advances in that area. Optical televiewers with lamps of different wavelengths of light imaging the borehole wall. What can that bring us? Evolution of the spectral induced polarization. Will it respond to semi-quantitatively to heterogenetic lithologies? Rugose boreholes with stratified borehole and formation fluids. These are all things that we might talk about at Exploration 2027, but it won't be me. Thank you. Yeah, I'm sorry I went overboard. No questions. Ask me later.